another thing I need to talk about for this kind of stuff. And the other is, we can also, when we're looking just at a categorical variable, we can also create confidence intervals for the proportion. Okay, and sometimes we just want to do that. Okay, and so all of these things can be done. You can use like the same data for a bunch of different things. Okay, so let's say we didn't make any kinds of hypotheses here. Okay. So remember, with a confidence interval, so a hypothesis test and a confidence interval, a lot of times we look at the same thing, but we're taking a different perspective. With a hypothesis test, we say, I've got this hypothesis in mind, and do we have data that either rejects this idea and supports something else, or not? Okay, that's how a hypothesis test works. The confidence interval, on the other hand, says, I've got no preconceived notions to start with. We're just going to gather some data, and let's see what the data says about the population. So when we did confidence intervals for means, we just took some data, we observed the mean of the sample, and we said, what does this say about the population? We can do the same kind of thing here, but with categorical data. When we take a sample, we get a sample proportion, and based on the sample proportion, we say, what does this say about the population proportion? So here we gather data. And we observe a sample proportion. So that sample proportion is P tilde. And from there, we create a confidence interval. Now, our book does something a little bit unique in most compared to other statistics textbooks, but we'll follow what it does. Okay, so this is just an aside, so you don't need to memorize this or anything or know this, but many other textbooks will say put p hat in the middle and go plus or minus the critical value, which in this case is z star times the standard error. And the standard error would be p hat times 1 minus p hat over n. Okay, so that's an aside, and I think that's how most textbooks approach this subject, but our textbook does something a little unique. Okay, but with good reason. So our textbook does something strange, and the reason why it does it is because, let's say you wanted to know, what percentage of people in the United States, I don't know, have some rare condition. Okay, so let's say, what percentage of the United States has, I don't know, jaundice or something? Okay, and so you go out and you randomly select 100 people. And maybe you select 100 people and 0 people have it. Okay. So you observe 100 people and 0 people have it, and you've run out of money. You can't survey any more people. Okay. Well, if you created a confidence interval at this point, your p hat is 0, and then your standard error, your p hat is 0 here, so your standard error zeroes out also. So your confidence interval is just 0, okay? But that's clearly not correct, okay? There's clearly more than 0% of the population has whatever condition you're looking for, okay? And the same thing happens if the proportion is extremely high, like close to 100%. It's something near 100%. Your p hat would be 100%, but then your standard error, when you do 1 minus p hat, ends up zeroing out, okay? So, so the book takes care of this problem by using something called the Wilson adjusted proportion, okay? And I guess Wilson was the guy who came up with this idea. It says basically, no matter what I observe, I'm going to pretend that I saw 4 more people or whatever where 2 had the trait and 2 didn't have the trait, okay? And so if I observed 0 people, 0 out of 100, I'm going to pretend that I saw at least 2 people with the trait out of an additional 4, okay? So basically, our adjusted sample proportion is, what letter do we use here? Y, okay? We take how many successes we see, and we add 2 to that, and then we add 4 to how many total observations we have, okay? So if this is our original data, is that y equals 0 and n was 100, my p hat would be 0.0, but then my p tilde or p squiggle would be 2 over 104, so basically 2%. Just a little bit off from 2%, okay? And then if our original data was y equals 50 and n is equal to 100, so if we've got 50%, then p tilde would be 50 over 100, which equals, and p hat would be 50 over 100, but p tilde would be 52 over 104, which is also 0.5, okay? So it kind of adjusts things so that, you know, if it's close to 50%, it doesn't change anything, or hardly changes anything. But if it's towards the extreme zones of near 0% or 100%, it brings those it brings it back to a zone where we can do a little bit more work. All right, is this okay? So using the Wilson adjusted sample proportion, it messes things up on the theoretical side a little bit to do something like this. So we're just going to stick with a 95% confidence interval. We lose a little bit of the flexibility here. Okay, so for a 95% confidence interval, using the adjusted sample proportion, we're going to go p tilde plus or minus the critical value, which is going to be 1.96, times our standard error, which is going to be the square root of p tilde times 1 minus p squiggle over n plus 4. Alright, so someone says, you know, I wonder what proportion of the Army is women, okay? And you say, okay, well, that's a good question. Let's, we'll take a random sample. And then, so we take a random sample of 100 people from the Army, and let's say we get 89 males and 11 females, okay? And then so we say make a 95% confidence interval for the proportion of females in the Army. Alright, so in this case, we have to figure out what P tilde, P squiggle. That's going to be 11 plus 2 divided by 100 plus 4. So I get 13 over 104. I get 0.125. So now I have 0.125 plus or minus 1.96 divided by the square root of 0.125 times 1 minus 0.125 over 104. So here I have 0.064. Plus or minus 0.064. Okay. So that gives me between 0.061 to 0.189. Alright. 95% confident. That the proportion of females in the military or in the Army is between 6.1% and 18.9%. And that's it. Okay, so that's for confidence intervals. Okay, so it's pretty straightforward, and I think we've talked about confidence intervals enough. So it's just a new process, but this time it's dealing with proportions. Okay. With that kind of data, you can do both confidence intervals or hypothesis tests. And so they, and we've already done hypothesis tests using the chi-square goodness of fit test. All right. The chi-square goodness, not chi-square goodness of fit test, but the chi-square test can also be applied to categorical, to see if there's relationships between categorical data. Okay. So now, relationships. So now we might ask the question, you know, is the proportion proportion of females in the Army different from the proportion of females in the Navy? Or is the proportion of, I don't know, history majors at UCLA the same or different from the proportion of history majors at USC or something like that? Okay, so we've got categorical variables, so we've got basically two groups, and within each of those groups we've got, or basically there's another category, and we're saying, you know, is the proportion the same or different? The proportion of, so proportion of whatever, okay? So we could say the proportion of blonde-haired people, persons, different for men and women.
Wait, quick question.
Yes.
Persons versus people. Is there a difference? Because you like corrected yourself, and I've always wondered that.
I don't know. I'm sorry. What did I say as
You
I'm
said
writing?
people, and then you wrote
Persons.
persons, so I thought maybe you had the secret.
Sometimes I write things and say different things. I'm sorry, does anyone know? Blonde-haired persons? Blonde-haired people? Different from men and women? I don't know. I'm sorry, I can't. That's not my area of specialty.
Fine.
Although I am fascinated by language too. Okay, so our the way we gather data here, okay, a lot of times it's summarized in a two-way table, okay, so, or a contingency table. Okay, so we might say men, or women, we'll say blonde, not blonde. There's an E after blonde, right? Is there a word without the E? Is that?
I think that's male, female.
B-L-O-N-D, is that anything? Nothing. There's no word for that. I feel like I see that too. Alright, so then, okay, how many men did we observe? Okay, 100. And we will say 20 and 80. And then let's say 20 women and a total of 32 and what is that? Did I do my addition correct? Legal correct. Okay, so this is our data. And then so we go, okay. We want to know, is the proportion of blonde-haired persons or people different for men and women? So in our null hypothesis would be that the proportion blonde-haired men is equal to the proportion of blonde-haired women. Okay, or symbolically, the probability of being blonde given male is equal to the probability of being blonde or the most simple blonde hair alternative is that, well, basically the opposite of the null here. Okay, so proportions are different. Okay. So if you say proportions are different, that would be non-directional. Okay. Using a not equal to sign. You could also make it directional. So this would be another possible alternative. So these two are not going to be the same. And the alternative, you know, you could put a less than sign. Okay, so you could put a directional alternative there also. Or not independent or something like that. Okay, but saying not independent would be non-directional. So, all right. So this is the data that we observe. Okay. And again, all of these questions, whenever we do a hypothesis test, is if the null hypothesis were true, what's the probability of observing our data? All right. So we've got to figure out, well, if the null hypothesis were true, what would we expect to see? And then we can go on and figure out how much our data deviated from what we expected. We saw a total of 220 people. 100 of them were male. 120 of them were women or female. And 52 were blonde, and 168 were not blonde. Okay, so let's think about this. If the null hypothesis were true, how many blonde-haired men would I expect to see? Okay. Well, what was the overall proportion of blonde-haired people? The overall proportion is 52 out of 220. So my proportion of blonde is 52 out of 220. Okay. So that's 0.23636 or whatever. And I would expect, if the proportion of blonde-haired males is the same as blonde-haired females, I would expect 52 out of 220, or whatever proportion that is, 0.23636, of the males to be blonde, right? So I would just take this proportion and I would multiply it by 100 to get the proportion, or the number of blonde-haired males that I'm expecting. So I would just do 100 times 52 over 220. And I get 0.23 let's just do 23.6. Alright, and over here I would do the same thing. I would do 120, and I'm expecting the proportion is 52 over 220. So I'm basically doing like an n times p in each of these things, okay? And I can do 120 times 52 over 220, and I'm getting 28.4. Okay. Technically, I didn't even have to do 28.4, or do the math here, because once I have 23.6, I know that there's a total of 52 people. So it's 23.6 plus some number over here has to be 52. And using that same logic, I can do 23.6 plus some number must add up to 100. So that some number must be, well, 76.4. And then, well, this is a little bit tougher. This is going to be 91.6. So that the columns add up, okay? But if you wanted to go through the expected, so for any given cell, the expected number is the column total times the row total divided by the grand total. Okay, and basically we're just taking the proportion of overall blonde-haired people total and multiplying it by how many are in that column. So that's how we get our expected numbers. So these are the numbers that we expected, and this is what we observed. So we've got to figure out how much did what we observed deviate from what we expected, and we do the chi-squared test for that. So the chi-squared statistic is still the same. We do the observed minus the expected squared over what we expected. And we're going to add this up for all 4 cells, okay? For all cells in our table. So there's going to be 4 of them. So I do 20 minus 23.6 squared over 23.6 plus, okay? And they're all going to be 3.6 squared over 28.4. And the next one maybe I skipped a step here, but basically if you do 32 minus 28.4, you get that, and 80 minus 76.4, you get that, and 88 minus 91.6, you get 3.6, okay? So in all of these, this one's technically negative. And it's not a coincidence, it has to do with the fact that once this number is determined, all of the other numbers are also determined. Okay, but I hope this isn't confusing. So let's do this. 3.6 squared over 23.6 plus, do this with all of these things. And I get a chi-squared statistic of 1.32. I was hoping it would be bigger. Guess not. Okay. All right. So now I just go to my chi-squared table, and when you're doing a chi-squared test to see if variables are independent or not. So chi-squared test for independence. The degrees of freedom is equal to the number of columns minus 1 times the number of rows minus 1. So here I've got 2 columns minus 1 and 2 rows So I've got 1 degree of freedom. And we kind of observed that, or as soon as we put in 23.6 for the number of blonde-haired men that we expect, the other 3 cells were automatically, they were locked into position. There was no ambiguity about what value those cells would be. So I've got 1 degree of freedom. So I go to my chi-square table with 1 degree of freedom, and the very first number is 1.64. And the p test there is 1.20. So if I look up 1.32, my p-value, I don't know exactly what it is, but I do know it's bigger than 20%. And so that says, if you were to take, if the proportion of blonde-haired men and blonde-haired women are the same, then anytime you take a sample of 220 people, you've got over a 20% chance that your data would look something like this or more extreme in terms of the proportions of blonde-haired men and blonde-haired women. In reality, I think the proportion of blonde-haired women is higher than blonde-haired men, just because more women choose to color their hair than general. But in terms of, but for children, it's about the same. A lot of times, I don't know, hair colors change over time. Things go. Okay. Let's see. What else do I need to cover here? What time is it? Oh gosh. Completely lost. Okay, so then, so these things can also get more complicated just by having more columns or more rows. Okay, so so if you had something else, such as level of education completed. Okay, this will be completed high school, completed 4-year degree, graduate school. Okay, and then we looked at income. So we say below 21 to 50, whatever. Okay. Okay, so you've got all these things. So now I've got 3 columns and 4 rows. You can still, because it's a categorical, we've got, this is a categorical variable, and this is also a categorical variable. We've turned income, which is normally thought of as a numeric variable, into a categorical variable. We can analyze this using the chi-square test for independence. Okay, so education level. Categorical variable. And then income turned into a categorical variable. And so we can, we're seeing if there's a relationship between two categorical variables. So we would use the chi-square test for independence. Okay, so that's still totally valid. Chi-square test. And the process is exactly the same. And we just use the degrees of freedom. How many degrees of freedom do we have here? 3 minus 1 times 4 minus 1. So now I have 6 degrees of freedom. And then the process to find the observed versus the expected just becomes really, really tedious. Okay? Because so I'd have all of my data. I would have 12 cells of observed data, and then I have to figure out the expected cells. So there's 12 expected values I need to come up with, and then I just have to add them all up. Observed minus expected, quantity squared over expected, basically for all 12 cells. But it can be done. And then you go to the table and you look up in the row for 6 degrees of freedom. So usually at a point like this, we would probably turn to the computer and say, you know what, 12 cells, figuring out expected values for 12 cells is a little bit too much work than I'm willing to do. So we go to the computer and ask the computer, figure out the chi-square test for me. Okay, so let me just, I'll just do a quick demo here. So this is what we've got, and do you guys remember what were? Let me just look at the numbers that are reported here for the military. Oh, blonde 20, 32, 80, 88. Okay, so in R, you can create basically a matrix, a 2x2 matrix, and use that as input for the chi-square test. Okay, and so the command that you're going to use is chi-square.ts.test, and it talks about what you want to use here. Okay. And it can be used. It can be used both for the goodness of fit test and the test for independence. Okay. So for the goodness of fit test, let's say what we wanted to know if a die was fair, okay? And so let's say these are our die rolls. Then let's say I roll the die 100 times, or I don't know, a whole bunch of times. I'm not even going to bother. And let's say I see the number 1 appear 20 times, the number 2 appear 23 times, the number 3 appears 19 times, and the number 4 22, and 5 17, and this 16 times. So these are the number of each category that appeared. Alright, and then what I want, so I'm going to do the chi-squared test. And what I'm going to put in is I'm going to put in die rolls as my original thing. And what I'm expecting is the probability to be 1/6 for each of these things. So you can just enter a vector of probabilities. One, two, three, 4, 5, 6, 7. So this says I'm expecting the first category to appear 1/6 of the time, second category to appear 1/6 of the time, third, and so on and so forth. So all of these are 1/6. And then I just say R, do your magic, and tell me. And so here it goes. Chi-squared test for given probabilities. Okay, that's the same thing as the goodness of fit test. And it tells me that my chi-squared value is 1.9231. The degrees of freedom is 5. And so my p-value is 0.8597. Okay, so this is not enough data to show that that my proportions are not met. Okay, so I would not reject the null hypothesis. And you can change that up however you want. If we want to do the chi-square test for the proportion of women in the Army, okay, so we could do chi-square.test, and here I can just put in directly the data that I observed. This would be 89 men, 11 women, and the proportions I'm expecting are 0.85 and 0.11. Okay, and then 0.85 and 0.15. Okay, and it says that. Don't need to do these the right things. Okay, so then and it goes through the test. Okay, so I think these numbers match what we got. I don't know if you can specify a directionality here. Okay, so with with R, I don't think you can specify directionality. So if you want a directional test, you've got to divide the p-value in half yourself. All right. The other thing we want to do is for a 2x2 table or for a matrix. Okay. So let's say we were dealing with you know, the blonde-haired thing. Okay. What we've got to do is we create a matrix, and into the matrix, I'm going to put in the 4 values that I observe, and the way R handles the observations is it goes down a column, and then once it exhausts the column, it then goes down the next column. So I'm going to put 4 values, and the order of the values that I'm going to put them in is 20, then 80, then 32, and then 88. And then I have to tell R that the number of rows is 2. Okay, and we can just double check that this is what our matrix looks like. Okay, so I put in the values 20, 80, 32, 88, and it creates the matrix just like this. And then so if you give R the chi-squared test, chi-squared test, and I type in blonde, it's going to automatically know that I want to do a test for independence, see if the proportions of each of these columns match up or don't match up. So chi-squared test for blah, and it gives me, okay. It does this continuity correction thing, okay? So I gotta say, correct equals false. Okay. Now it matches up what we get. Okay. So the continuity correction is fine, okay? It's just we didn't learn it, so when you do it this way, your numbers aren't gonna match up, okay? So chi-squared test, blonde, and then you don't do the correction. Okay, correct equals false. And I believe this is the number that we got, right? When we did it. Please, in your notes. Did we get 1.34? Or did I add it up wrong? We got 1.32, so I must have messed something up, I think. 1.32, 1.34, it's close enough. I think it's because when I did it, I rounded off a little bit. Okay. And you can put in giant tables also, okay? So if you had, if we were doing this income thing, and somehow we created a table, so you have to, so the thing to remember is you gotta make it into a matrix, and I'm just making up numbers here. I just need 1, 2, 3, 4, 5, 6, 7, 8. Okay, I totally was making up numbers here. Okay, well anyway, this is our income matrix, and we want to know, is this do the chi-squared test here, and it does it super quickly for you, okay? And it does degrees of freedom 6, and here it tells me, so some of my numbers must be way weird, okay? So it tells me my chi-squared statistic is 772, which is incredibly large, okay? And it tells me my p-value is less than 2.2 times 10 to the negative 16, okay? So that's like 15 zeros and then a 2. So the probability, if this categorical variable has nothing to do with this categorical variable, the probability of just taking a random sample where we get a distribution like this, the probability of that happening by random chance is less than, 15 zeros, 2, 2, okay? So it's incredibly small. So this would tell us that at least one of our things are wrong. Okay. I didn't do correct equals false, but it somehow didn't do it. Anyway. Okay. So you don't have to worry about this. Okay, I'm not going to assign you a lab, but you can do the chi-squared test on R, and if you ever forget, just remember chi-squared.test, and then you can always do R help for chi-squared test, and it'll give you some examples, some guidance there. Okay, that's actually all I have planned for today, so we'll finish a little bit early, and you guys have a good week. We'll see you guys next week.
Close this out of time.